Hello friends, I J.Prajapati welcome you in lecture number 6 on partial differential equations. So we were solving Lagrange quasi-linear equations, and as I discussed, there are 4 different types to solve Lagrange auxiliary equations, and we have seen type 1 in previous lecture. Today we are going to discuss type number 2 for solving Lagrange auxiliary equations. So in this type we have those type of partial differential equations which are Lagrange equations, and in which one solution u can be obtained by directly comparing fractions in Lagrange auxiliary equations, and second solution v can be obtained by using this first solution u, which we obtain by directly comparing fractions. So we are able to find out the one solution by directly comparing fractions, and second solution is not possible by directly comparing the fractions. In those type of cases we will try to see whether we can obtain second solution by using the first solution. So we discuss this with the examples. Suppose we consider this example number 1. So you can see given equation is del z by del x, that is small p, plus 3 into del z by del y, that is 3 into q, equal to 5z plus 10 of y minus 3x. So if we compare with Lagrange auxiliary equation, Lagrange quasi-linear equation, then it is in this form of Lagrange quasi-linear equation. So we can apply that method of solving Lagrange equation. So we can start with Lagrange auxiliary equations. So if we compare given equation with this standard form, then we can see capital P is 1, that is coefficient of small p, capital Q is coefficient of small q, that is 3, and capital R is right hand side, 5z plus 10 of y minus 3x. So we start by writing Lagrange auxiliary equations. R dx divided by p, that is capital 1, dy divided by capital Q, and dz divided by 5z plus 10 of y minus 3x. So if we observe fractions 1 and 2, then we can directly compare fractions 1 and 2, because we have differentials dx and dy and remaining things are constants. Now if we observe fractions 2 and 3, that is fractions containing dy and dz, then x must be absent if we want to compare these two fractions, fractions 2 and 3, then there must not be any term which contain x. So you can see the presence of x here. So we cannot compare second and third fractions. Similarly, if we want to compare fractions 1 and 3, then y must be absent, but y is also there. So we cannot compare fractions 1 and 3. So we can compare only fractions 1 and 2. So one solution is possible by directly comparing fractions. So taking first two fractions, or taking fractions 1 and 2. One and 2 of Lagrange auxiliary equations, we have dx divided by 1 equal to dy divided by 3 or this we can rewrite as 3 dx equal to dy, and this is separable ordinary differential equation of first order. And we know how to find out this integration. This solution of this equation can be obtained directly by integrating both sides with respect to x and y. So it is 3x plus some arbitrary constant equal to integral of y, dy is y. So it is not necessary that you put arbitrary constant on right hand side. It is our choice. We can put it either on left hand side or on right hand side. So from this I obtain y minus 3x equal to c1. So therefore first solution of Lagrange auxiliary equations is u equal to y minus 3x, which is equal to c1. Now we are not able to compare remaining two fractions. So now if you observe here, we have y minus 3x here, and if we observe the first solution, then it is y minus 3x equal to c1. So if we use this y minus 3x equal to c1 in this last fraction, then we will have dz upon 5z plus 10c1. So that we can compare with any of these two fractions, either with fraction 1 or fraction 2. So what we are doing is we are using the first solution obtained to find out the second solution. So we first take any two fractions, either fractions 1 and 3 or fractions 2 and 3. So suppose I consider fractions 1 and 3. So first I write down fractions 1 and 3 are taking first and third fractions of Lagrange auxiliary equations that we have denoted by 1. We have dx equal to dz, and this I have to see here, dx upon 1 equal to dz upon 5z plus 10 of y minus 3x. So dz divided by 5z plus 10 of y minus 3x. So because here differentials are dx and dz, y must be absent here. So now we put y minus 3x equal to c1. From first solution we can put y minus 3x equal to c1. So we obtain dx equal to dz divided by 5z plus 10 c1. Okay, what we are using? We are using first solution obtained, which is y minus 3x equal to c1. Now this is 10 c1 is constant, so this is separable. So we can find out the solution directly by integrating. So integrating, we get integral of dx with respect to x is x. Integral of 1 upon 5z plus 10 c1 is log of 5z plus 10 c1 divided by coefficient of z, which is 5, plus arbitrary constant, that is c2. So here we are using the formula of integration. I hope you are familiar. I just write down the formula. We are using this formula, integral of 1 upon ax plus b with respect to x is 1 by a ln ax plus b. So instead of x, here variable of integration is z, and here coefficient of z is 5. A and B are constant, so A is 5 and B is 10 C1. And now after integrating, we finally put C1 equal to y minus 3x. So therefore x equal to this I can rewrite as 1 by 5 log 5z plus C1 is replaced by y minus 3x plus C2. So therefore this we can rewrite as x minus 1 by 5 log of 5z plus 10 of y minus 3x, which is equal to C2. So our second solution is v equal to x minus 1 by 5 ln 5z plus 10 of y minus 3x. So in this way we can obtain the second solution by using the first solution obtained. And once we find out two solutions of Lagrange equations, Lagrange auxiliary equations, the general solution is the general solution of given equation is phi of uv equal to 0, or we can write u equal to phi of v or v equal to phi of u, and after that we have to put values of small u and small m. So in this way we can use the first solution obtained to find out the second solution. We consider one more example. Here given equation is small p minus 2q equal to 3x square into sine of y plus 2x. So as usual we have to start with Lagrange auxiliary equations. So Lagrange auxiliary equations are dx divided by coefficient of small p, which is 1, dy divided by coefficient of small q, which is minus 2, and dz divided by right hand side, which is 3x square sine of y plus 2x. So we give this number 1. Now here also we are able to compare fractions 1 and 2, and we are not able to compare fractions 2 and 3 because here we have dy and dz, so x must be absent. Similarly we cannot compare fractions 1 and 3 because in fractions 1 and 3 differentials are dx and dz, so y must be absent, but here y is also present. So we are able to find out one solution by directly comparing first two fractions. So we write taking first two fractions of 1, we have dx equal to minus dy divided by 2, or this we can rewrite as 2 dx equal to minus dy, and if we integrate, this is separable equation, so after integration we obtain 2x equal to minus y plus constant of integration, which is c1, and this is y plus 2x equal to c1, and this implies the first solution is u equal to y plus 2x, which is c1. So you have observed this y plus 2x equal to c1, this we have observed in this Lagrange auxiliary equations. We have y plus 2x here in the last term. So we can replace y plus 2x by c1 here. So y will be eliminated, or y will be hidden by putting y plus 2x equal to c1. So then we will have dz upon 3x square sin c1. So sin c1 will be constant, and after that we can compare this dz with dx, because everything will remain in terms of x and z after putting y plus 2x equal to c1. So now we will take fractions 1 and 3. So now we write that taking fractions, or taking first and third fractions, taking first and third fractions of 1, we have dx equal to, first fraction is dx upon 1, that is dx, and dz divided by 3x square sin of y plus 2x. dz divided by 3x square sin of y plus 2x. So we have differentials are in terms of dx and dz, so y must be absent. So for that we replace this y plus 2x by c1. So we have dz divided by 3x square sin c1. So we put y plus 2x equal to c1, that is using number 2. So here we have to mention that we are using equation 2, which is y plus 2x equal to c1. Now this is easy to integrate. This we can shift on left hand side. Sin c1 is now constant, so 3x square sin c1 dx equal to dz. So 3 into sin c1 is constant, and x square dx equal to dz. So this is separable ordinary differential equation. So we can find out the solution by direct integration. So integrating, we obtain here 3 sin c1 is constant, and integral of x square will be x cube by 3. So 3 will also cancel out. So we are left with x cube sin c1 equal to integral of dz is z plus arbitrary constant, suppose c2. And therefore we put, after integration we put c1 equal to, c1 was y plus 2x. So x cube sin y plus 2x equal to z plus c2, or this we can rewrite as x cube sin y plus 2x minus z equal to c2. Therefore the second integral is x cube sin y plus 2x minus z. I have to write it again. X cube sin y plus 2x minus z. This is nothing but second solution, which we denote by small v. So therefore v equal to x cube sin y plus 2x minus z. And finally, hence the general solution is phi of u comma v equal to 0, where u is y plus 2x, and v is x cube sin y plus 2x minus z. We can put their values also. Therefore phi equal to y plus 2x comma x cube sin y plus 2x minus z equal to 0, and phi is an arbitrary function. So in this way we can use the first solution obtained to find out the second solution in Lagrange auxiliary equations. So so far we have discussed type 1 and type 2, and in the next lecture we will discuss type 3 of solving Lagrange auxiliary equations and its examples. After that we will come to the last type 4. But these are just for conveniency. Depending upon the given partial differential equation, you have to decide first whether it is Lagrange Quasilinear equation or not. After that, to solve Lagrange auxiliary equations, we have divided these different types. So you can decide whether which type is possible for particular given differential equation. So in the next lecture we will discuss type number 3 and its examples. Thank you very much.